Welcome back to the course in Nuclear Medicine Physics. Today we have an exciting topic, a method of producing radionuclides in particle accelerators. We'll look at the different ways of how radioisotopes are produced in accelerators. Finally, we'll look at a bit of the math that gives the reaction rate that occurs when you produce radioisotopes in accelerators. I hope you enjoy this video and let's get to it.
So another method of producing radioisotopes is by the use of particle accelerators. So the idea behind particle accelerators is that they're going to accelerate charged particles to very high energies. And then we're going to take these accelerated particles and we're going to direct them to a target material with the hopes that this initiates a nuclear reaction. And in that nuclear reaction, we're expecting that the daughter or one of the daughters coming out of it is that radionuclide that has some interest to us. So it's similar to neutron activation in the nuclear reactor. It's just that, well, we're accelerating some other particles. Now, to be able to penetrate the Coulomb field from the nucleus, the energy of the particles that we throw into the nucleus is typically in the order of 10 to 20 MeV. So look, let's look at some of these reactions. So we have, for example, the PN reaction in which we have our target. We're gonna bombard it with a proton. And okay, so now we have a proton inside that nucleus. So we gain a proton, we change the element, and our mass stayed the same because a neutron came out of that nucleus. This one example of a reaction, and let's say our element Y or this isotope of the element Y is of interest to us. Okay, yeah, that's what I just said. Well, there's another reaction that we can accelerate a deuteron. So a deuteron is a proton, is a hydrogen nucleus that has a proton and a neutron, and well, we can have deuteron bombarding this target. We gain one proton, but we also gain one neutron, and we have Y. And one neutron came out. That's why the mass only increased by one, not by two. Yeah. So those are just example of reactions. There are many more many more reactions that we can use. So we can bombard with a proton, and two neutrons are going to be released, or bombard with a deuteron, and 3 neutrons are going to be released, or deuteron, proton, deuteron, 2 neutrons. We can even use alpha particles as this particular example. We bombard these, we can obtain indium-111. So let's see if you guys are more or less understanding this notation of nuclear reactions. So if you look at that reaction of silver to produce indium-111, which would be true?
While people are answering, we did have a question. Given all the difficulties and uncertainties, are the two methods from nuclear reactors used in nuclear medicine instead of the particle accelerators?
Yes, so we use both in nuclear medicine. Some of the isotopes that we use come from the nuclear reactor, some others we do produce them in cyclotrons.
Yep.
And we'll get there. Give me 1 sec, because I have some tables at the end. Okay, I'm gonna stop this poll, and I'm gonna share the results. So yes, most people got it right. We're using a target that is silver 109. We're bombarding it with an alpha particle. We're obtaining indium-111 as a product, and in that process, 2 neutrons are released. So A, B, and C, we have all those conditions happening. So the answer is D. It's all of the above. And yeah, most of the people, as I said, answered right. So it looks like people are understanding this notation. That's good. If you didn't answer right, just try to take a look again and ask me questions if it's still not clear. Okay, but I just want to emphasize this. So anything in particular that can be pointed out about the accelerated particles in these reactions? So we have protons, we have deuterons, we have alpha particles. What can we say about those particles? I already said a couple of slides before, but just want you guys to keep it in mind. Yeah, people typing in the chat. So what should be brought up to our attention about these particles on the left? What is common for all of them? Okay, yeah, so some people saying are charged, they're most stable, all have charge. Yeah, exactly. So yeah, so that's where I wanted to get at. So all of these particles are charged particles. So in these particle accelerators, we need those particles to have a charge, otherwise we wouldn't be able to accelerate them. So in the nuclear reactor, we have the neutrons. A neutron has no charge, but in particle accelerators, we need to be able to use some type of interaction to accelerate them, and that's going to be the electromagnetic interaction. We need a charge. So this is an example of a particle accelerator, and it's the most widely used, which is called the cyclotron. So just to point it out, okay, how does the cyclotron work? Let me just see. Okay, what you see here on the right is like a transversal view of a real cyclotron when it was built. This is a cyclotron that we have here in Vancouver at a center that is called Triumph. I think it is the biggest cyclotron in the world, but here you're looking from inside. But okay, so a cyclotron works by having 2 semicircular metal electrodes, which are these 2 that I'm pointing here. And because they have the shape of a D, they are typically called Ds. So this is 1D and then second D. Now they're placed between the poles of an electromagnet. So we're gonna have some magnetic field in there. And this is represented by this B. So B represents a uniform magnetic field. So this B in this case is, let's say, coming up, is perpendicular to the D. We place the ion source at the center, and then this is going to be in vacuum. There's a gap between the 2 Ds, and between that gap, we're going to put an electric field. Now, that electric field is going to accelerate the particle in one direction. Now, because we have charged particles and we have a magnetic field, that particle is going to change direction. So when the particle gets here, we're going to change the direction of the electric field, and we're going to accelerate a little bit more, and so on and so on. And it's going to gain more and more energy. That's why it's going to go in a bigger diameter circle. And at the end, we're just going to get that particle out of that cyclotron, and we're going to focus in on bombarding the target that we're interested in. So I have these, because you're going to stop seeing me for a moment, but I just want to clarify these. Let me see what's going on. Okay, so just keep in mind, if you have, let's say, a charged particle, it can be a proton. And if we put that proton on an electric field, E, then that proton is going to feel a force in the direction of the electric field. If for some reason our charged particle is negatively charged, then it will just go in the other direction. So that's why when we have this region here, we have a let's say a proton there, if the electron field is pointing to the left, then that particle is going to gain an acceleration to the left as well. When it comes down here, we're gonna change the direction of the electric field to feel the force going to the right. And for the magnetic field, let's say we have, this is just representing a magnetic field going into the page, into the slide. We have now, say, a proton that has some velocity going to the right. And I don't know if you've seen, but okay, that follows an equation that it has, that the force is related to the cross product of the velocity and the magnetic field. So, well, for that, you would have to use your right hand rule. So velocity goes to the right, magnetic field is going inside of the page. So this will feel a force going up, and that's what's gonna cause this particle to move in circles. So, well, in this case, we have the magnetic field going up. Let's say the particle, let's look at the particle here. Let's say the particle is moving to the left, magnetic field is coming out. So, well, in this example, the force will go down and it's making it to go in circles. I just wanted to clarify that because I don't know if everybody has this knowledge from physics, but that combination of electric field pushing forward. Sorry, I lost my mouse. That combination of the electric field pushing forward, it increases the kinetic energy of the particle. The magnetic field does not change the kinetic energy of the particle, it just makes it turn around so that then when it comes here, we can push it again. Are there any questions about this? Looking at the chat, making sure. Okay. Well, cyclotrons don't work very well when particles reach relativistic speeds. So in that case, we'll have to synchronize the way in which we change the frequency for this electric field when they move at higher speeds. So the synchrotron synchronizes that chain of frequency when it comes relativistic. It's not a case for what we do in nuclear medicine. Like, we typically just use cyclotrons, but if you want to accelerate particles at much higher energies, then you might want to think about how you're going to change this frequency of the electric field when you change the direction, and well, that way you can achieve higher energies. And that's what happens, I think, for example, in CERN, when you have the biggest synchrotron. Okay, what can we say about radionuclides produced with cyclotrons? Well, here we typically add positive charges. So similar to what we were saying for the nuclear reactor, in which we had an excess of neutrons, here we're typically adding positive charges. So there's gonna be an excess of protons. So these radioisotopes will tend to decay by beta plus or electron capture. Again, they want to get rid of that excess of protons. The atomic number is changed, so cyclotron generated products are typically carrier-free. So you start with a target of one element, your result is a different element. So you have a different element that typically is radioactive, so you have a higher chance of getting a carrier-free product. Now the cross sections, we're gonna see what that means in a moment. Let's say the probability of having these reactions happening in the cyclotron is less than in nuclear reactor. So what this turns out to be is that our result has smaller quantities of that desired product compared to if this was going to happen in a nuclear reactor. Are there any questions about cyclotrons? Okay. So let's look at some considerations in the production of radioisotopes. So we can think of this, okay, and this is coming back to something that I left on hold at the beginning. You can see, okay, if we want to produce a radioisotope, well, that's going to give us, that's going to be the reaction rate. What's the rate of production? How many of these new nuclei am I producing per unit time? That's going to depend on what we call the beam current, which is given by I. So how many particles per second are hitting the target that we're putting for it to hit. It depends on the cross section of the reaction. So the cross section is basically how likely is the occurrence of an interaction. If I throw a proton to a particular nucleus, how likely is that proton is actually going to go into the nucleus? And it's not exactly a probability because it has units of centimeters square, but it gives us basically the area of interaction that has units of barn. So 1 times 10 to the 20 minus 24 centimeters squared is something that we call a barn. It depends on the density of target nuclei that you have in that target. So how many target nuclei do you have per centimeter cube of that target? And it depends on the thickness of the target. So these are things to consider when we're trying to produce radioisotopes. Now you can think of I as being the current, like how many neutrons are hitting the target if we're talking about a nuclear reactor, or how many protons are hitting the target if, for example, we're talking about a cyclotron. But let's suppose that we want to produce a radioisotopes that decays with a decay constant lambda. So again, in nuclear medicine, we're going to use a nuclide that is radioactive. So it's going to be decaying. So this is our production rate. So how many particles do we have per unit time? It depends on our production rate. This is what we're gaining. This is what we're producing. But this is what we're losing because it's decaying. So we can reorganize this equation. If I bring this to this side on the left, and we can multiply by T on the right. Now, looking at this equation, I'm suggesting, okay, let's change variables. Let's call y equals r minus lambda n. That's what we have down here. So we look at that, then dy would be minus lambda dn, keeping the production rate constant here. So then we can see, okay, let's replace dn, then would be dy over minus lambda. That's what we have up here. The denominator is what we are now calling y, and dt is still dt. So we can reorganize this a little bit more. So dy over y, and then I move this lambda to the other side. It's minus lambda dt. I hope you guys are following. So if you solve the differential equation, then you basically obtain this, which is the integration constant, and we can write in terms of exponents as b e to the minus lambda t. But again, remember our changing variable. So I'm gonna, y is r minus lambda n, e to the minus lambda t. And let's just think of a case in which the radioisotope of interest at t equals 0, we have no radioisotope of interest. In that case, if we look at this, okay, this is, okay, basically, this is our answer. I'm just taking this answer here and looking at t equals 0. So at t equals 0, this is b, n equals 0 because we have nothing at the beginning. So in that case, our constant is the same as r. And okay, so that gives us the number of nuclei that we're producing would then follow. Okay, you can simplify this a little bit more. You can bring this to the other side, and so on and so on. And it follows this equation. And I hope you can take a look at this in detail at home. Now we know that the activity, as Armand showed in the previous lecture, is related to n by lambda, by that decay constant. So we can write the activity we're producing, and the activity of that radioisotope of interest, if we're using a production rate R, is going to be like this as a function of time. It's going to follow that equation. So, well, we can plot that, and it's going to look something like this. So this particular example, we're just thinking that we're in a nuclear reactor trying to produce molybdenum-99 by bombarding a target. So we put a target in the nuclear reactor and we're gonna use those neutrons, and well, as time goes by, we start to get more and more molybdenum. But then, because the molybdenum at the same time is decaying, you can see that at some point it's just basically gonna stay constant. It's like, yeah, we can keep bombarding this target for months, and and our activity is not really gonna change. So if we bombard by 1 half-life of molybdenum, we get this. If we bombard 2 half-lives, we get here. We bombard the target by 3 half-lives, we get here. So what I'm trying to show is that there's not much to be gained by irradiating that target for more than 2 or 3 half-lives, because it just stays. And that has to do because of the decay of that, in this particular, the decay of molybdenum-99. And then, okay, well, but we can keep growing. But then when we remove the target from the beam, from that neutron flux, then that molybdenum is just gonna follow the radioactive decay that it would normally do. So what I'm showing here is, this is when we're producing it. If we were keeping irradiating, it will still keep going up a little bit until, well, it's just gonna have an asymptote there. But here, this was basically an irradiation of 7 days. We take the target out of the nuclear reactor on day 7, then our molybdenum in that target starts decaying following a 66-hour half-life. So this is, okay, so we're gonna get into the generator in a moment, but we know that molybdenum is gonna become technetium-99 following this decay. So this is exactly what's gonna happen. Is the nuclear reactor, we're gonna put a target there, we're gonna get some molybdenum-99, and then we're gonna have some days to prepare a sample and ship it to a hospital for them to then extract technetium-99 from this molybdenum. So typically irradiate by 7 days, maybe 1 or 2 days, extracting the target and purifying it and extracting the molybdenum-99, putting it in a container and shipping it to the hospital. So maybe by the time you ship to the hospital, you have this amount of activity of molybdenum-99. And as it travels to the hospital, it keeps decaying. And then inside the hospital, of course, it keeps decaying. So once in a while, you need to get a new supply. Now, something that I want you guys to have a little bit of caution is, I just showed you guys this formula on the left for the production of radionuclides. The book just has the equation written slightly different, but is the same. Okay, well, this is the activity. I should remove this part from here, but okay, the cross section is the same. The only difference between these two equations is where we're putting the volume. So I was describing the current as the number of particles per second hitting the target. And in the book, we just changed it a little bit for the number of particles per second per centimeter square hitting the target. So that's why here you see a volume, here we just see a delta X, and it's because that centimeter square that I'm missing here, or here we put in the volume, and here is just included in this density. So just take a little bit of caution when you look, and you can just say, okay, but these formulas are different. No, they're exactly the same. It's just that we're moving the units a little bit on the definition of the current.
Carlos, we did have a question in there just to clarify. A question was, isn't the thickness of the target considered in the cross section? And maybe you can explain what the cross section really means, to perhaps clarify that point.
I'm just gonna try to draw something here. I'm not the best at drawing, but I'm gonna try.
Mhm.
Okay, let's say you have a target there and you're gonna start throwing some particles. So this is our beam hitting, let's say, this region in that target. So this area here will be our cross section. It will be how much of the area of that target is our current covering. But now you can think that this is a volume of a target. So you can have one slice, one very thin layer of the target fired by another very thin layer, and so on and so on. So then this would be a thickness. It would be a cross-sectional area here. It's just I don't want to use A because it gets confused with activity. Let's say S for surface. This is the cross-sectional area, but you have still target behind that surface. You have some thickness of it. I don't know if, does that answer the question?
Yeah, I mean, it's taken into account, but the question was, why is it that in the cross section, that term for the cross section, I think that's what the question is. Does that account for the thickness? I mean, the thickness, essentially, the volume of the target is being considered. But I think when people look at, I think when people look at the equation and you go through this exercise, you know, at first when you go through the exercise, these terms may not be quite clear, but just go through them one by one, and I think you'll see, you'll get the answer.
So maybe to clarify a little bit better, if I multiply this equation by the surface divided by the surface, that's basically multiplying by 1, right? And I can just put one of those terms here. So what's going to happen is that this surface by the thickness is our volume on the right, and then this current is now our current on the right. So this is the current per centimeter square, and then this is the volume. So that's exactly what's happening there. Instead of, it's basically just multiplying this equation by 1, but using the surface divided by the surface.